The next type of exponential equation that we're going to be learning about is the equations with uncommon bases, and we cannot even rewrite them with common bases or the same base. For example, 4 to the x equals 15. Now, if this problem was 4 to the x equals 16, well then I can rewrite 4 to the x equals 4 to the 2 and then set my exponents equal to each other, and this is a very fast problem. Although I don't have a 16, and 15 here cannot be rewritten as 4 to the anything. So because I cannot rewrite them with common bases, we're going to be looking back at the steps that we talked about earlier. First step says to isolate the base with the variable in the exponent. Next, we're going to take the natural log of both sides, and that's going to move the exponent into the coefficient using the power rule. Then we're going to solve for x. So the big key here is we're taking the natural log of both sides. So on our first problem, 40x equals 15. Is the base with the variable part isolated on one side of the equation? Yes, it is. An example of one of these that wouldn't be is our third example. E to the 3x is our base with our exponent, and we have a multiply by 30 and we have a minus 3, so that's what the first step means. Isolate the base with the variable part all by itself on one side of the equation, which we have on this first problem. The second step says take the ln of both sides, the natural log. So I just put the ln in front of both sides of the equation. What this does is it takes my exponent. Using the power rule, I can replace the exponent in for the coefficient, and I get x ln 4 equals ln 15. Notice this is a multiply. In order to solve for my x now, I need to then undo the multiply by ln 4. The opposite of multiply is divide, so I divide both sides by ln 4. And my answer is x equals ln 15 over ln 4. I want you to leave your answer in exact form, such as this ln 15 over ln 4, but just in case you need a decimal approximation for another class that you're taking, I want you to be able to do that. So in order to approximate ln 15 over ln 4, I use the ln button, 15 divided by, type the ln button again, 4, and then hit enter. It looks like my approximation to 2 decimal places is 1.95. Let's look at our next problem. Again, my base with the variable exponent is already isolated. So that's step 1. Step 2 says take the natural log of both sides. So I'm going to take the natural log of the left equals the natural log of the right. The reason we take the natural log is so that we can take the variable out of the exponent and, using the power rule, write it in the coefficient of the ln. Remember, that's a multiply. Because this is a multiply, in order to isolate my x, I am going to divide both sides by ln 9, which leaves me with negative x equals ln 2 divided by ln 9. And I've almost got that x isolated, but I really don't want the negative in front, so I'm going to multiply both sides by a negative 1. Which leaves me with x equals negative, or the opposite of, ln 2 over ln 9. The negative could possibly go in the numerator or denominator or out in front. If I'd like to get a decimal approximation, I just type negative ln, it opens up a parentheses for me, 2, close my parentheses, divided by ln 9, close my parentheses, and I have a decimal approximation of negative 3 point, this 5 is going to round that up to a 2, negative 3.2. On my last example, my base with the variable exponent is not yet isolated. So first I want to get rid of the minus 3 and the 40 multiplied by 40. So I'm going to do the opposite using my linear skills. Now I have to get rid of the 40 coefficient, and to do that I just divide both sides by 40. And now I have e to the 3x equals 6. Now I have my base with my variable exponent isolated on one side of the equal sign. So now I can go to step 2, which says take the natural log of both sides. The reason I want to do that is so that my variable exponent can move out of the exponent into the coefficient of my ln. So I have 3x times ln e equals ln 6. Next, I'd like to isolate my x variable. But before I do that, I see one other thing that's a little bit interesting to me that I can reduce, and that's ln e. We know that ln has an invisible base e, and whenever I take the ln, any number, of itself, you have the value 1. ln e is equal to 1 using our properties that we learned in the previous section. If you don't believe me, we can always type it in the calculator. The way we would type ln e would be use the ln key. In order to get the e, I have to use second ln, and I don't really need e to the anything. I could write e to the 1, close my parentheses, which does get me 1. So ln e to the e is equal to 1, which is a little redundant. We don't really have to write that. Finally, to solve this, I'm going to divide both sides by 3 to solve for x, and my answer is x equals ln 6 over 3. To get the decimal approximation, I'm going to type in ln 6, close my parentheses, and divide by 3. And it looks like my decimal approximation is 0.60. Next, we'd like to look at logarithmic equations. Again, there are two types of logarithmic equations that we'll be working with. And I want you to know that if there is more than one log in the equation, whether it's on the left-hand side or right-hand side or both, then the bases must be equal. To understand the two different types, type 1, the logarithmic equation, can be expressed as the log base sum b of some argument equals c, where c is a constant. It's kind of a mouthful, so usually I just say log equals number. So the log has to equal some number. For example, log base 3 of x equals 4. Or ln x equals 7. Or another one, log x plus log 3 equals 4. Notice in each of these examples, there is a constant, a term that does not have any log in it. And that's the requirement to be of this first type, log equals number. The steps to this type are to first condense all your logarithms to a single logarithm using the rules of logarithms that we've learned in the past. Step 2 says to rewrite the log equation as an exponential equation. Solve and check all of your solutions to make sure that they do not make your arguments 0 or negative. You cannot have a zero or negative argument because the domain of a logarithmic function is 0 to infinity. So you can only have arguments which are between 0 and infinity, not including 0. And that's for all log expressions. The second type of log equations that we'll be working with today are equations that can be expressed as the log base b of some argument equals the log base b of another argument. Again, that's a little bit of a mouthful, so I reduced that to just log equals log. Some examples of that would be log base 7 of x equals log base 7 of 42. Another one would be log of x plus 3 equals log of 2x minus 4. And the last one, log x minus log 4 equals log x squared. Notice that in each of these examples that I just gave you, we have a log on the left equaling a log on the right. There are no terms that have a constant like the type 1, where we have equaling a constant on the right hand side. Both sides have logs. All terms are log form. Even on our second equation, log of x plus 3 equals log of 2x minus 4. Again, my bases are the same, and I have a log on the left equals a log on the right. And lastly, even though I have more than just two logs, every single term, log x, log 4, and log x squared, all have logs in them. There is no term that has just a constant. If a term just had a constant, then that would be of type 1. Type 2 has all terms being in log form. Our steps to solve this are very similar to the steps of the first one. The first step is exactly the same. Condense your logs to a single logarithm using the rules of logs on each side of the equation. Step 2, on the other hand, is the one that's different. Instead of rewriting the log as an exponential, you can only do that if you have log equals number. If you have log equals log, you're just going to set your arguments equal to one another, which is similar to type 1 exponential, where we set the exponents equal to each other. Here, we're just setting the arguments equal to each other. Step 3 is the same as type 1. We have to solve and check our solutions to make sure that the arguments are not 0 or negative. And the reason that they can't be 0 or negative is because the domain of any log expression is from 0 to infinity for the argument. So therefore you cannot have solutions that make your argument 0 or make your argument negative. And we will be checking all our work on our problems.